I went through the entire test, all the question bank. I picked out all the questions that were pertaining to these two chapters, which are attached to the back. There's two different packages, one for chapter 9, one for 10. And then I went through the two chapters in the book, and I kind of rewrote it a bit, and then included all the answers in all my material for all the questions, because some stuff isn't kind of clear in the book and doesn't answer a question directly. So I went and I just rearranged it a bit to match that. So you should be able to find every answer for all the questions within my material that I gave you. I've also tried to highlight some of the important facts that will show up on the test as well. You'll see it in bold in my my notes. So it's a little point form, but there's still a lot of stuff to cover. So I'll start off. Again, my name is Matt Dunlop. My call sign VE3BRD. It can stand for bird, as Bruce calls, because I'm in fly planes and copters, or beard is what actually I did it for. Yeah, I'm original. And feel free to email me if you have any questions. You can reach me at nerd@mattcave.ca, and I'd be happy to answer any questions you have if I can. So I'm not going to profess to be an expert on the topic. Electronics is a hobby of mine, and I have a great appreciation for it. And I can take you through here, but if you start getting into quantum mechanics, then I might not be able to answer your questions. So that might be a little above my pay grade. So starting out tonight, we're going to be talking about electronics. What do? They control the flow of electrons so that we can gain some intelligence out of them. We can transfer them from one place to another, and we can receive something intelligent out of that. Or we can convert it to do math, computers, lots of different things we can do with it. The purpose of all this is just to cover the theory that you need to know to pass the test. I'm not going to go into super depth. I'm going to try to get to the point where it's understandable how these devices work on a high level, but I'm not going to get into the actual formulas and things that you would need to know to actually design a circuit. That's not required for the test. For the advanced level, that'd be more pertinent. We started off, you've talked about conductors in the previous lessons. A conductor such as copper has the valence, or the outer shell of the atom has many electrons, and they freely flow from one to another, and they easily give them up and move from each other. A semiconductor is a little different, where they're built up into a crystal structure, and they were built to the point that I'm going to turn this on here. Speaking specifically to silicon, which is used in many semiconductors, the silicon generally has 4 electrons in its valence shell. However, if you have 8, which is what they prefer, it actually makes the atom stable, which will then actually turn it into instead of a conductor, it will actually stop the flow of electricity. It'll be an insulator. Let's see if this is working here. So as you can see, this is a conventional drawing of an atom with electrons. It's not the current theory of the way they are, but for visualization purposes, we have the outer valence shell, which has 4 electrons naturally. But when we create silicon wafers for semiconductors, we combine them into a lattice. And each one has 4, but when they're connected to the one beside it, it creates, they fill up and create 8. And when there's 8 electrons, it becomes very stable. The crystal becomes so stable that it becomes a good insulator. So that doesn't sound like a very good way to conduct electricity or to make anything intelligent happen with it. So what they do with it is they introduce a contaminant, which they call doping. They dope the material, and by adding a material such as phosphorus or boron, they can either add, as in this situation, they've added an atom of phosphorus, and it has an extra electron. So now it has one more electron, so it can give that one up, and it can become a conductor of sorts. And that creates an N-type semiconductor. N for negative because it has more electrons. So it has a negative. For a P-type, this is the case we use boron. It has one less, creates a hole as they call it. So it can attract an electron. So it can become a conductor in that respect. And that becomes a P-type semiconductor. Just the back check, getting a little ahead of myself. When they are mixed together in this state, this is a covalent bond, meaning that the structure is completely stable with the 8 electrons circling it. I'm going to say a lot, I apologize. So as it says here, when doping they use a material that has one less or one more. So for example, like I said, the phosphorus has one more electron and boron has one less. Which creates as I said earlier, the N-type, which has extra valence electrons, creating a negative charge. The P-type has missing valence electrons, hole, creating a positive charge. Silicon and germanium are the most widely used forms of semiconductors in computers and electronics. It's freaking out. I don't want to cover the material that fast. Sure, bring your own remote, you'll look cool. Oh, my big fingers touch it. So, I've already covered this. There we go. Oh, pages are a bit off here. So basically that's how they create the two types of semiconductors, N and P. So now what can we do with this? Well, I'm gonna have to put this down. You can create a junction. A junction, in this situation, we're going to show a PN junction. So we take some P material, we take some N material, stick them together, put some diodes on the end, and it creates a diode. But how a PN junction works, take my handy dandy board, I'm instructed to bring it out here. Just going to draw. You're going to be amazed at my beautiful drawing skills. I'm going to edit myself and drawing a transistor. Alright. Look at an eraser. See now I have to draw it neat. With this P material, N material. So the P material is sandwiched beside the N material. The P material will contain holes, as we discussed in the P material by using boron, for example. It'll have it won't be complete, every atom won't have boron in it. It won't be all boron. It just there's a sum, so it creates the potential for flow of electrons. The N material is more negative, has extra electrons. So what happens is even when we even when this isn't connected or have a power source connected to it, it actually creates a small current in itself. The electrons are naturally drawn towards the holes that are in the P-type. So they won't be able to draw the whole thing, but it creates a little bit of an area that we call the let me get my notes here. And then I should know this depletion zone, sorry. So in the depletion zone, the electrons will satisfy the holes. And as we saw from the previous slide, when we had the silicon, when it had all 8 electrons around it, it created an insulator. So in this state, right now, with these electrons satisfying these holes in this section here, it actually creates an insulator. It won't allow electricity to flow through here. Okay? So if we were to take, for example, an electrode and we put it here and here, we can hook up a voltmeter to this, and this would actually create a small potential difference. Depending on the type of diode this would be, it could be up to 0.7 volts. Obviously it doesn't have a lot of storage capacity, but it'll be there briefly for a second. So now what can we do with this? Well, we've got we want to be able to control the flow of electrons. That's really the important thing that computers need to process all those ones and zeros. So we have our electrodes connected to each side, to our P and N. If we take a power source, such as a battery, let's say, and we connect it up, this is just kind of high level, because if we don't have resistance in here, we'll blow up this circuit, but just for demonstration's sake, we hook up the positive side to the P material, P for positive, the negative side to the N side. What happens is electrons will naturally want to flow from the negative, and they will replenish the electrons that were taken from the silicon on this side, and they will then supply the holes this side, and thus they will eventually start moving across until all the holes are filled, allowing electricity to flow through. However, if we reverse this, we make this negative, it actually, the negative will cause, I guess we're going to call it pressure, because the positive will want to draw these electrons towards it, and likewise the other side. This will actually cause the depletion zone to expand, because it's going to draw the electrons out, and in that respect it actually cuts off the flow of electricity. So a diode will allow electricity to flow in one direction and not the other. So that's the simple form of a PN junction. There's different types of diodes. We have one thing that you need to know for the test is there's Zener diodes. The Zener diodes are a little bit of a special case. This is a Zener. They have a lot of extra doping material in their P and N junctions, and they allow the current to flow in the opposite direction if you overcome a certain voltage level. So we don't need to get into the detail of that, but you need to remember that for the test. A Zener diode, because of that property, can be used to be a power regulator in itself for small currents. So they will ask you that question on the test, guaranteed. By the way, the other thing you need to know is when we have our positive to positive or negative to negative, and electrons are flowing through this circuit, this is called forward biasing the circuit. This is a forward bias. And the other way is reverse bias. Forward is when things are flowing. Another use for diodes, again taken from the questions. I'm going to be hitting this thing all night. Took my boots off because I was kicking it so hard I was almost knocking it over earlier. So now I'm just going to break my toes. So diodes are used frequently in the demodulation process in a signal. You're going to need to remember that for the test. It's located, it's on the in my notes. I do remember that. Diodes, they have two ends. One end is called the anode and one's a cathode. The P material is the anode. So this is the anode over here, this connector, and this is the cathode here on the negative side. The way I remember it myself, in my head I have more of a visual memory as I think of a diode and a PN junction, and I think AC is in alternating current. That's just the way I remember it. Not sure if it'll help you or not, but hey, works for me. Other types of diodes that you've seen frequently are LEDs, light emitting diodes. So they function in the exact same way that a regular PN junction does, except when electrons are flowing through them, they generate light, which we can use to signify something, or we can have little LED displays, LED TVs. They're all diodes. Now we'll talk about the the schematic symbol for a diode. Wow, that's terrible. Fix that. I have no motor control. So this is the anode is connected to the back of the arrow. The cathode's on this side. Now the way that this arrow is pointing is it's pointing towards the flow of electricity in conventional, not in electrical theory or In modern theory, we look at electron flow. In conventional theory, they used to believe that electricity flowed from the positive to the negative. And that's why the arrow points this way, because this is the positive side, this is the negative side. Conventionally, that's the way it would go. However, in the real world, electrons flow from negative to positive, so it's actually the opposite. So hopefully I just confused you. There's the Zener diodes. They because they have the extra ability to be reverse biased so much that they will start flowing electricity. They have their own diagram. They have the little extra squiggly lines that denote a Zener diode. I didn't put that in there. I just realized I forgot that. But that's the symbol for a Zener diode. You don't need to know that for the test, but just FYI. You will need to know what a Zener diode is, though, what it's used for. Any questions so far? Glossy-eyed? Perfect. So now that we have a PN junction, great, we can control the flow of electrons in one direction. What can we do with this? Well, we can take our handy dandy little PN junction and erase it. Where am I on my? Push this back for a second. So I think I covered all these points. P material. The depletion mode in the zone in the germanium is 0.3 volts. And so we measured it in a silicon diode, and it was 0.7 volts if we hooked up the voltmeter leads right into the material. Depletion zone expands when the flow stops the flow of electron, and it's reverse bias when you hook up the negative to the positive, positive, negative. Diodes are used to convert AC into pulsating DC. I'll get into that a little more once we get into the power supply section about how that actually works. And what single diode can be used to create a half wave, multiple diodes can be used to create full wave. We'll cover that in a little bit here. Next, what can we do with these lovely little junctions? Well, we can stack them. We can create transistors. Transistors is where we can start doing some real cool things. We have two different types of transistors. We have a PNP or an NPN, and it really is just what materials we have. So we have P material with an N material in the middle, then a P material, PNP, so it's positive, negative, positive, and we have NPN, which is the negative, positive, negative. So I'll draw some schematics later, and I'll show you exactly how they work. However, these are the symbols for them. A PNP, NPN. Again, we're using, there's someone knocking. Someone let me in. So the arrow on here again is following conventional electronics theory, and that the electrons flow from the positive to a negative, but in reality, in the NPN it's negative. It flows from emitter to base, and the opposite from base to emitter. So I don't know if that'll help you remember or not, or confuse you more, but you'll have to remember that for the test. You will have to remember which way electrons flow. Again, the transistor is actually short for transfer resistor. And the other way to remember which one is which is PNP. You see the arrow. It permanently, what is it? It's permanently in, points in permanently. PNP, so the arrow points in, and never points in is NPN. So if you look, it always points out. So NPN never points in. It'd be better if the N was the first letter in the word, but I didn't make that one up, so don't blame me. Transistors can be used as a switch or an amplifier. We'll get into that a little more in a bit. And again, to NPN. Maybe I should get into that now. You know what? Let's do that. So I'm going to draw a transistor. So in the transistor, we sandwich different P and N materials, just like the NP-PN junction, except now we have two junctions in this case. So we essentially have two diodes connected together. And what we can do with this, is we can use this one here, the base. This lead here is called the base, and we have the collector and the emitter. Now, if we hook up a circuit to this, let's say. If we hook up circuit positive, negative, what happens is, again, before we even hook this up, getting ahead of myself again, without power connected to it, it creates two depletion zones automatically. Of a depletion zone here, of a depletion zone here, just like in the PN junction, where the electrons will fill these holes in this area and will create an insulator, and these electrons here will fill the holes in this area and create an insulator, thus stopping the flow of electrons in two locations. So the magic happens if I connect power to the collector and emitter. Because of that, it's not going to allow electrons to flow through at all. They're completely blocked in two locations. So what we do is, if we connect our base to a positive voltage, what it allows us to happen between our base and emitter, it allows electrons to be pulled from the battery or power source and replenish the electrons that are being pulled here in the depletion zone, and we'll start breaking down the depletion zone. The depletion zone will then start flowing electrons. Some will come down this way, then it'll allow them to move over here, filling these holes and allowing electrons to flow all the way across. So if we have enough voltage applied, positive voltage here to the base, it will completely break down this barrier and allow electrons to freely flow through the NPN transistor, and basically use it as a switch. So if you've had something to break this connection here, then you can control this flow of electrons through these two gates. And for a PNP, it's very similar, except it's exactly the same but opposite. So in this case, we have these two junctions, we have positive material, negative material in the middle, and it's creating the zone. It's filling these holes over here, creating another insulator, and again over here. Now this time we have to apply a negative voltage, so this has to be positive, this has to be negative, so it's the exact opposite. I'll hook up a negative, yeah, I guess same spot because I reversed the battery. And now it will cause electrons to flow through here, filling up these holes and allowing electrons eventually to flow across here and the other way, opening up the flow of electrons across the similar, just use the negative as opposed to a positive in the NPN. Still with me? Yeah, everyone can see I'm not too much in the way? Okay. So that's the basics of how a transistor works. It's not that complicated, really. It just gets down to knowing how much voltage you can apply and how much goes where. So that's those are PNP, NPN. I'll just catch up to my notes here. See if I'm moving too fast, too slow. If this would tell me what time it was.
In your example,
yep.
Why would you do that?
I'll get to that. I'll show you once we get down to power supplies. You'll see I have some real world examples down there. Okay. Just remember. Remind me. I should probably take a drink. So we have transistors that we can use as a switch to control the flow of electrons. We also have FETs, or field effect transistors. They do a very similar job, they do it in a slightly different way. So there's two types of field effect transistors, the N and P. I'll show you why. I'll draw it on the board in a moment. They have different electrodes. They have a gate, a drain, and a source, as opposed to a collector, base, and emitter. And they provide similar functions, but we'll have to review that. You'll need to know how the gate, drain, and source is compared to the collector, base, and emitter for the test. There will be questions on that. I've on the in the notes I have a chart for you as well that shows you where they all are. The source is where the electrons enter the gate. The drain is where electrons leave, and the gate is where it's controlled. I'll show you how that works in a moment. The gate acts kind of like the base in a transistor. But the way these guys work is they have a channel. I'm going to reverse this. I'm going to say a source, and the drain is down here. This is the gate. So we have two types. We have an N type and a P type, and what classifies that is the material that makes up this channel here. There's a channel that goes directly across from the source to the drain, and if it's made up of N material, if it's mostly negative, then it's an N type FET, and if it's positive, we filled up with holes making it a positive or a P type FET. The way these work is when there is no voltage applied to the gate, this is a conductor. It'll allow electrons to flow through. Let's hook up a battery to this and see what happens.
You said when there's no ground or when there's ground?
Yeah, it's the opposite of a transistor in that respect. So the gate's not connected. We have electrons are going to flow freely through up to its power rating, obviously, depending on your circuit. So now we want to do something. Well, the way this works is the gate, when you apply, depending on the type, if we have an N type, we put a positive. Oops, it's positive. We connect the gate to a positive source, and we are going to, instead of, if you remember back when we were talking about diodes, the PN junction, holes. We have a depletion zone that's between the P and N material, and we connect up a negative to the P material, which is the positive material, and we hook a positive. This is reverse biasing this junction, which actually causes the depletion zone to actually grow, because it's drawing the electrons from the N material towards the positive and vice versa, the opposite side. So it actually causes this zone to stretch, thus making this material in the center insulator, and the bigger the insulator, the more electrons is going to stop from flowing through. So in this case, what we're going to do is we're going to reverse bias this. And when we put in when we reverse this, it causes the depletion zone to form across the gate. So it starts forming across, and the more electricity we apply to this, the depletion zone grows. So you see it's creating a pinch point in the flow of electrons through here. You apply enough power, and it'll create a depletion zone that crosses the entire junction and actually stops electrons from flowing all the way through the device. So in that sense, it acts as a switch when you apply enough. So they do a similar function, except we reverse bias a FET and we forward bias the transistor to make it do something. With an N type, we would again, it's positive for a P type. These would be all holes. We would hook this up to the negative to reverse bias it.
So, just so I'm clear.
Yep.
So one is used to do something after the power gets so big, or it gets so much voltage. The other one is to stop it after
yes.
the voltage.
That's how you can use these are the switch, or you can use them as, I'll show you in a little bit how you use them as an amplifier to amplify signals. Because this gate here requires a lot less electricity to actually make the depletion zone go across than the amount that's flowing through here. So you can control a large flow of electrons with a relatively small flow of electrons. I guess that's an important thing I should have pointed out. That's the same with the transistor. The gate voltage is very low compared to the amount of voltage that can go from the flow across the emitter to the collector, or the collector to the emitter. So you can use, for example, I'll get to it. I have my example. Hey, look, it's next. Perfect. So again, I highlighted some things on this page that are answer questions on the test. To reduce the current flowing in a FET, you increase the reverse bias voltage on the gate, which causes this pinching to actually happen, which stops the flow of electrons through. When it's reverse biased enough, it's called the pinch off voltage, because it pinches it off. The other thing to note is because this is a conductor, in theory electrons can flow in either direction, but manufacturers, they have the drain and source, they've doped the material in such a way that the electrons flow better in one direction than the other, so just follow their directions. If they say it's a drain, use it as a drain. Okay. So what can we do with these devices? Well, maybe some more racing. It's satisfying. I used to do a lot of this when I was in school. I was teacher's pet. Race the board!
Thanks so much.
Thanks, Jason. So we can use a transistor for gain. Now, gain, when we're talking transistors and FETs, will amplify voltage and current. It won't amplify, it won't change the frequency of a signal, but it will amplify its the power, the wattage. The way it does that, as I was saying a moment ago, is we can have a power source which is much higher voltage, let's say 12 volts, and the input signal is 5 volts. So the input signal can control a 5 volt, with 5 volts can control 12 volts flowing across the transistor. So that, well, if you're, I'm not very good, I like drawing. I'm just gonna tie something to my hip so I can just hold it. Sorry guys. I don't even know why I'm using that. So let's do a transistor. This is my favorite, NPN. Let's hook up a 12-volt source. I'll have a separate. These aren't to scale. So we need a signal. We'll use our this is time, voltage. So we have a signal. It's my perfect sine wave, and it's 5 volts. This 5-volt signal is too low. We will need to hook it up to a 12-volt speaker. So it's not high enough. So what we can do is we can use an NPN transistor in this case, and we can apply this 5-volt signal, which will be this guy here, this 5-volt source, to our base here. So our emitter, I don't think it's going to be neat. Anyway, so what happens is, as we know, when we apply the voltage to the base of the NPN transistor, it causes the depletion zone to break down as the negative electrons will be drawn through, and replenishing the depletion zone here causes the flow to go all the way across. But if we don't reach the maximum amount of voltage that requires to completely bridge the gap across, it will actually restrict it. It creates resistance. So in essence, when we take a voltage that's going into the base, and as it's climbing, it's allowing more, and then it's going to allow more and more and more through. So it's going to use this lower 5 voltage signal, which is required to the 5 volt, let's say, is the max. To keep it simple, if we applied 5 volts directly to this, it will fill this completely up, allowing electrons to flow right across. But if we put 2.5 volts across here, it's gonna allow half the voltage to flow through. So in that sense, we'd have a 12 volt source going through the collector and emitter. With the 2.5 volts, it'll allow 6 volts across. So it cuts it in half. So if we have a waveform, and as it's fluctuating, as it's going up, it's going to allow more of the 12 volts across, and it's going to match this waveform, but instead of based on 5 volts, it's now going to be 12 volts. So it'll be a much larger, much more powerful. That's how we use transistors to create gain. Any questions? Make sense? And
where would the speaker be hooked up in that circuit?
In this circuit, the speaker would be over here on the collector side.
And then that would go back to the negative of the 12 volt?
That's correct. So this is a positive, so this guy goes in here. Negative, so we're gonna actually have a diagram. It would take the place of where the resistor is in the diagram.
Okay.
I'm getting a little messy here.
Now is the just again, sorry.
Yeah.
The 5 volt.
Yeah.
Is that's on its own circuit, or is it connected to the?
It's connected via the negatives. Sorry, this is positive, and the 2 negatives will be connected.
Oh, okay.
So they're grounded together, basically. This is negative. Yeah. Me good at drawing.
It makes sense.
As long as it makes sense. So there's a circuit that goes here. It's created here between the 5 volt source. It controls this section here. And then the 12 volt source really is across these two. But they're both connected here at the negative end. So the negative of the 12 volt, the positive, which goes through the speaker in this case. Wow, that's awesome. Not sure what
But
that
the
looks
12
like.
volt would in the updated would be up top, right?
Yeah,
Yeah. Okay.
exactly. Or if you look at my the second one under as a switch. Break those legs off. You can see the 0 voltage here would be connected back to the 0. There's a positive side that goes in the GPIO. This is I do a lot of work with microcontrollers, and a lot of the microcontrollers I use are 5 volts. And I want to control something that's much higher volts. For example, I have a cooling fan, it's 12 volts. If I hook that up to the 5 volt source on my microcontroller, it's going to draw too much, it's going to potentially kill my microcontroller. The very best, the fan won't spin very well. It's only 5 as opposed to 12 volts. So I use an NPN transistor. I'm not going to use a pen on the screen, that'd be bad. And I hook it up to the general purpose I/O on the Raspberry Pi, for example, which is 5 volts. And I'd have the load being the fan, or an amplifier would be a speaker. And this would be 12 volts up here. And we'd have 5 volts coming off the GPIO. The 0 is grounded on the Raspberry Pi, on the negative of the Raspberry Pi, this example. So when I tell the Raspberry Pi that I want to turn on the fan, it's going to put 5 volts across the base of this NPN transistor, which is going to forward bias the emitter, causing electrons to flow at a maximum amount, so allowing the full 12 volts to control my fan. So there is a resistor in here, which if you do use the Raspberry Pi, it's 1K. That's the actual resistor you want to use if you're doing that, for 12 to 5 volts. In the sense that it's acting as an amplifier, the GPIO pin on Raspberry Pi can be used to not only do 0 to 5 volts. It can do pulse width modulation, so it can actually, instead of just going from off to on, it can go in a duty cycle. It can go off, on, off, on, off, on multiple times a second. And by doing that, it'll be turning this switch on and off really fast. And if I do it for, let's say, a 50% duty cycle, it will give 12 volts to my fan 50% of the time. My 12 volt fan will now essentially run half the speed. So it's using it as a switch, a very fast switch, but we can use it to modulate the speed of real world devices. Or they either do the same to modulate the brightness of a diode, is they use the pulse width modulation. They frequently turn on and off the transistor, which will control the LED, because LEDs, they last a lot longer if you use PWM. Because let's say for 50% duty cycle, they're still quite bright, and you'll double their life, because they do have a life expectancy.
It's almost like a dimmer.
Yeah. But because, for example, the fan needs 12 volts to run, by doing this, I'm just turning the 12 volts on, off and on really fast. So it's getting the current it needs to run, but it doesn't get up to speed, to full speed right away, so we'll keep it happily running at half speed. How am I doing for time?
But giving you double the battery life at half speed.
Yeah,
Yeah.
it will. It will extend your battery life, yep. We do the same in my airplanes. By controlling the motors, it's all through PWM, which I'll show you guys on the break. I'll show you what I got into ham for. It's all this stuff over here. I'll show you on the break or after. 7:48. Do you mind if we take a break now?
No, sure.
Well, actually, you know what? I have one more part. I'll do the transistor characteristics. So we have transistors characteristics. Obviously, these examples I showed you, they don't have any resistance in them. I'm hooking up direct loads to these things. That would just blow them up in the real world. We need to be able to restrict the voltage going through these. They have certain limitations. So the enemy to transistors is heat. Heat causes them to break down. Heat will release the magic pixies and the magic smoke. They want me to incorporate pixie into the speech, so there you go. When you're looking at a data sheet, they'll list these. We have I have some transistors and some FETs here if you guys want to look at them, the different types. And we have heat sinks for transistors, because the warmer a transistor gets, it also affects the depletion zone, because as you can imagine, heat excites things, expands things, it causes things to happen. So when heat starts getting applied to a transistor, it starts behaving erratically if it gets too hot, because it can cause electrons to do all kinds of fun things. They get excited, super excited. Breakdown voltage is the maximum voltage that may safely be applied between the electrodes under any condition of operation. So the manufacturer will say, for example, 50 volts is the maximum breakdown voltage of this device. If you go beyond 50 volts, that device is going to overheat. It's going to release the magic smoke. The maximum voltage is the maximum operating voltage that may be safely applied. So the maximum voltage would be the amount you can safely use without causing it to overheat. In some cases, you will still require a heat sink, but they'll list that in the sheet. Maximum current is the maximum amount of current the collector can handle, and the collector again will be on the outside. Is how much power you're going to be, the large power you're going to be controlling through the transistor. The maximum power is the maximum amount of power the device can get rid of in the form of heat without damage. When exceeded, a thermal a runaway happens. It's kind of what I was speaking about. A runaway is when my device starts getting too hot, the depletion zone starts getting destroyed just because the electrons are excited, and it can cause a complete breakdown of the transistor, and it could completely open the gate. It can open the gate down through the base, which can destroy your expensive $35 Raspberry Pi or any other larger devices you connect it to. So these things are cool. They create gates. You can control circuits. You can turn things on and off. You can amplify signals. But in a single device, okay, I can turn on a fan with my Raspberry Pi. That's kind of neat with one transistor. But it's when we take these devices and we put thousands, millions, billions of them together into a circuit that we create logic circuits. We create integrate circuits, as in a microprocessor or a microcontroller. For example, the iPhone has 2 billion transistors in it, approximately. So that's a lot. 2 billion of these. It's crazy. So by using the simple principles as a switch, they arrange them in such a way that they create logic gates, AND gates, NOR gates, not, and which will create your ones and zeros, which will answer math equations, which eventually gets to your graphics. Scales up. 2 billion. There's to my hand. Oh, that's not so big in here. So there's different packages that they come in. I put some pictures there. It's for your reference, and you don't need to know those things for the exam. Sorry, it's small. It's supposed to be bigger on my sheet. But if you're going to be looking into electronics and building small circuits, these are good things to know, because when you're doing order sheets online, it's good to know what a dip is, dip socket as opposed to a DPAC or a P-dip and all those things. They'll have different spacing, and they're important.
You're turning channels, please.
Cool.
Almost done. No, it's good.
And that concludes the course. Whoa, whoa. See, it's getting too hot. It's getting excited. Sorry, I have bad humor as well.
Huh.
My friends will know that. Thanks, Mike. So I think now would be a good time to take a break.
Sure. Great.
Thanks, guys. I'll see you in, 15 minutes?
Yeah.